A very good morning to all of you. Today we are at lecture 13, Control Engineering EI 503. Right? Now, what is the topic today? Route stability criteria. So today we will be going to discuss the stability criteria in time domain mainly, and that topic is route stability criteria. Now, say what are the different subtopics? Condition for instability and the marginal stability. Okay, so we have the set condition for the instability as well as marginal stability. Just overview that we have already analyzed or discussed in the previous class. Now, what is route or which criteria to actually find the absolute stability of the system? Okay, as well as generating how the route array will be generated and what is the interpretation of that array, as well as what will be the interpretation with the system stability with that array that we will have to determine through the route coverage criteria. And route coverage criteria special cases. For special kind of systems, there are certain difficulties arising conventional route array, then we will move to the special cases. So how to handle the special cases that is already observed through route criteria. Let's move into the slides. So condition for instability and the marginal stability. First observation. What will be the observation one? Observation one is that the system is unstable if all the sign of the coefficients of the denominator of closed loop transfer functions are not same. That means what I want to say. That is, if you are getting for a system having the transfer function, having the PS, that is basically suppose certain value of the zeros. Okay, there are the poles. Suppose in the polynomial form. Okay, 2s cube plus 5s square minus 2s, suppose plus 1. Now, what I'm talking about here, for unstable system, what is observation? Observation is that all signs of the coefficients of the denominator of closed transfer functions are not same sign. That means what I am talking about, this is plus 2, this cofactors of S2. This one is plus 5. This one is minus 2, this one is plus 1, right? So what we could say, these are not seen with same sign. That's why that may be there's a probability of this transfer function that will be represented as a unstable system. Now, what is observation 2? Observation 2 is if the power of s are missing. That means suppose this denominator polynomial having the power, suppose 2s cube. Instead of we have 5s squared, there is 5s plus 3, suppose. This is the denominator polynomial. This is the denominator polynomial as a function of s. We can represent 2s cube plus 5s plus 3. That means here the power of s is missing. Index of square that is missing, right? So that's why s are missing from the denominator of the closed loop transfer function. Then the system is either unstable or that may be the marginal stability. Frequently it is unstable. That is for the case of marginal stability. Okay, these are two observation. These are two experimental observation that may be observed through different kinds of experiments. Okay, now what if all the coefficients are positive and no power of s is missing? From where? From this conclusion, two scientists, Raut and Harwich, define a criteria, prescribe a criterion, establish a criterion to get the stability analysis of the stable system. That means system is stable if there's a, depending on certain condition. This is called basically Raut-Harwich criteria, developed by Edward Raut. Okay, and he was actually in the English, and I love Harwich. He was basically German. Okay, so these two scientists worked over that and having the criteria, fixed up the criteria for the stable system that is called round harvest criteria. Okay, So it is obviously time domain analysis. While we are going to the topic, then we can realize. Okay. Now, what is the method encounters memory? So through that method, if we progress our numericals or experiments, so what we get? This method tells how many closed loop system poles are at the left half of a screen, left half of a screen, or right half of a screen, or on the geometry axis. That means it's very versatile. See, what are the closed loop pole positions? That is in the left half, or in the right half, or in the geometry axis. What is the count that may be represented through this method? Okay, so again I am repeating, this method tells how many closed loop system poles, that means closed loop poles, are in the closed loop poles means what? The basically the solution of the characteristics equation. Okay, solution of the characteristics equation, roots of the characteristics equation. And that is basically in the left half or right half or geometry axis. And what is the methodology they adopted? That is construction of the route table. So first of all, we need to construct a table and that will represent basically route array. First column of that table, that is basically representing route array. Okay, so we need to construct first a route table. That is the first step. We need to construct a route table and then interpret the route table, the sign of enter of the first column. That means we will be looking at the first column only. That is called the route array. That is called route array. Okay, so we will be looking for the route array. So through the route table, we will observe the route array. So what should be our observation? The sign of entries of the first column gives the information about the stability of the closed system. That means, is it right hand, left hand, or in the geometry axis? That may be observed through the route array. Okay, let's see how it will be observed. Now moving to the next part. Let's take an example. So this is the common representation of, suppose I have taken the highest order 4. Okay, so it is the numerator polynomial. This one is the denominator polynomial. That is basically representing the characteristics equation of the system. Okay, what is for the closed loop? That is g divided by 1 plus gh, right? Now this is the transfer function of the system. Now, if 1 plus gh, there's a denominator polynomial, that becomes 0. So we are getting basically the characteristics equation. So from this characteristics equation, see, I have observed here a4 is to the power 4 plus a3 s cube plus a2 s square plus a1 s plus a0. That was the denominator polynomial, characteristics polynomial. So we are getting the characteristics equation if this equals to 0, set to 0. Okay, so from that, this is the characteristics equation, and the roots of that characteristics equation is nothing but the closed loop poles, right? We know that concept. The roots of the characteristics equation is the closed loop poles. This is basically pole representing 1 plus gh, that factors, right? So roots basically nothing but the closed loop pole, right? Okay. Now, how to construct the route table? So first of all, you have to write what are the index of s. So s column. That is s to the power 4 starting with and end with s to the power 0. This is s to the power 0. So we are writing here s to the power 4, s cube, s square, s1, and then s to the power 0. S to the power 1, s to the power 0, right? And what is the methods? Let's see. So first of all, we are starting with s to the power 4. So what is the cofactors? That is f4, right? And leaving s cube, we will move to s square. So what is the cofactors we are getting? A2. Then leaving s, so we are just keeping one factors, okay, one order. So we are getting only s to the power 4, then we are taking s square cofactors, then we are taking s to the power 0 cofactors. So what we get? A4, A2, A0. Now come to the next row. So for the next row, let me clear this bit. Next row, we will start over there. So s cube, so leaving s square, we will consider s to the power 1, then we have s to the power 0, so leaving this one, we have no other factors. So what we have here, s cube. So s cube correlates with a3, right? Then we have one order missing, a1, then 0, as because there is no factors. And then uh, we have to generate basically the next one. So this is basically the layout. Then we will move to the next part. Okay. So what will be the cofactors of basically this row entries, this row entries, and this row entries, that will be in my, that is included in my next slide. Let's see. Then what we observe for this characteristic situation is, see, that was presented in the layout. So generating the route table. So what is we got in previous slide, we got A4, A2, A0, A3, A1, A0. Okay, right? These are two rows. Now for a square, so how to generate it? Okay, how to generate it? It's very simple. Delta. So how to determine determinant of this one? Let's see, just reverse of that. So A4 A1 minus A3 A2. Better just move to that part. It is minus something, that is A3 A2 minus A4 A1, right? So we will look at the matter. So we are concentrating over A3. This is our center point, right? So how to generate next entry? A3, A2 will be multiplied, and then minus of A4, A1, right? Divided by A3. Okay, so which one is our center? A3. So for this column to generate, A3 is our center. So everywhere in the denominator, see, all are A3, right? So this is our center. So while we are finding the delta, so how to find delta? A3 A2 minus A4 A1 divided by A3. Okay. Now for the next column entry, how to find? A3 A0 minus A4 into 0 divided by A3. Just like the previous case, but we are just multiplying this column entries with this column entries. So A3 A0 minus A4 into 0, because there is no cofactors, divided by H. Just keeping this minus sign. So we need to start from the center into this A2, just diagonally, then A4 A1 divided by H2. Similarly, A3 A0 minus A4 A0 divided by H2. Similarly, for the next factor, there is no column elements present. So A3 into 0 minus A4 into 0 divided by H2. Like this way, we will continue. So we are getting here B1, B2, B3, and that is 0. Similarly, for the S1, what are the cofactors? How could you find? Okay, so let's say then, as like as the previous, as same as the previous, we will start with that column right now, just before the S to the power 1. So we are getting here B1. So new center is our B1 now, center point. Okay, so we just so what is the cross factor? Diagonal factor is A1. So B1 into A1 minus B2 into A3 divided by B1. That we will get as C1. Similarly, B1 into 0 minus A3 into 0 divided by B1, that we will getting next factors. Similarly, as there is no factor aside over there, so we are getting here 0. Now, as we are getting C1, then C2, then C3, so we will calculate now for B1. So how to calculate? Then again, new center is C1. So like this way, it will continue. Okay. So for the C1, we are getting C1 into B2 minus B1 into 0 divided by C1. So ultimately, what we will get? We will get for s to the power 0, and that will continue. Okay. Now s to the power 0 is the lowest order. So that's why that table ended over there. Like this way, we will continue, and we will get general representation of the route table. Then from where we can easily get which one is the first array, the first column entries, that is basically identified as the route array. That is basically identified as the route array. So from after generating the route table, all the entries we made, then we can identify the first column as route array, right? Now, any row of the route table can be multiplied and or divided by the positive constant. That means whenever there is the, suppose there's the constant, same constant is everywhere in this entry. So we may again repeat S3. Okay, S over 3. So that may be just divided or that may be just multiplied with some positive constant. Okay, so we are dividing here by 2. Okay, that is, then the column entries will be A3, A1, A0. Suppose we have half everywhere. Suppose 3 by 2 here. Suppose here it is 4 by 2. So what we could do, 4 by 2, no, sorry, 5 by 2. So what we could do, here we can multiply with 2. So same factor will be multiplied to get the linear or better simple representation or analysis or further calculation. So we may divide, but in that case all the row elements that should be divided with the same positive constant, or that may be multiplied with the same positive constant. Okay, let's clear my sketch and we are moving to the next part. So how to interpret now? As we got now the route table or route array we have identified. So it is more general for the nth derivative equation. So we will get this kind of denominator polynomial and this kind of addresses equation. This is the general representation of the route table. So same route table for the fourth order I have mentioned previously, and that is for the nth order. So what you get here, A0, A2, A4, A6, shipping one factors, A1, A3, A5, A7. So like this way for the next, what you can say, index of S, we are getting B1, B2, B3, C1, C2, that will continue, and then ultimately for the S to the power 0, we are getting A. That is a general observation. Okay. So from that table, now we have to analyze what we have to interpret. A system is stable if there are no sign changes in the first column of the route table. That means this one is basically the first column, right? That is basically representing as the route array. So route array entry is A0, A1, B1, C1 up to AN. Okay, so the system is stable if there are no sign changes in the first column. So what should be our observation? We have to look not only on the values but also the sign. Okay, but also the sign. So if there is no sign change, it's fine. So it will be declared at instant stable system. But if there is a sign change occurs, suppose we are getting A0, A1, fine, all are positive, and B1 is getting negative, again we are getting C1 positive. Then all are positive, suppose continuing all are positive. So what is our observation? A0, A1. So while system is we are moving from A0 to A1, there is no sign change. So obviously A1 to B1, then there is one time sign change. Then B1 to C1, then again there is sign change, another second time sign change. So we are getting two times the sign is changing. Okay, so that's why what we can say here, the number of roots of the polynomial that are in the right half is equals to the number of sign changes in the first column. So if there is a number of sign change that we have observed two times, that's why what should be our resolution? Our resolution is there will be two right hand pole exist in the system. There will be two right hand pole exist in the system. So for the stable system, we are getting no sign change in the all the column entries. All may be positive, all may be negative, but there should be no sign change. But if there is any sign change occurs, so what should be the number of sign change that we have to encounter? That we have to count. And that basically encounters the number of right hand side pole. So system having, for this specific example, the system having two right hand side. Let's see to the more example numericals. We may observe what is the route criteria. Let's see. Okay. So we are moving to the next part. So example number one, what we have observed, it is basically GS 1000 divided by S plus 2 into S plus 3 into S plus 5. So we are getting here all are in the left half of S plane. Okay, it is for the open loop system. Now, while is given HS as equals to unity, so it will become closed loop system. So for the closed loop system, so transfer function we have observed, that is s cube plus 10s square plus 31s plus 1030. Okay, now let's see how to observe the route table. So this is the characteristic equation, denominator polynomial, that is s cube plus 10s square, that is that should be the basically in power. Okay, 31 is plus 1030, that is equals to 0. So accordingly, what we will get? 1 for the first column, s cube, then s square, then s to the power 1, then s to the power 0, right? So there is no other index of s. So starting with s cube. So what is the cofactors? 1. Okay. Then skipping s square. What is the cofactors of s to the power 1? That is 31. So 131 we got. Then skipping this one, we are getting 0. So 131, 0. For the first column, we are getting all the entries 131, 0. Similarly, for the second column, we are starting with s square. So what is the column entry first? 10. Then we will observe 1030, right? Then we will get 0. Now for the s square, we are getting 10, 1030, and then 0. Okay. So see what I said to you, that the route array, if there is the common multiple factor, so you may divide with that common multiple, right? So what you can say here, dividing with 10. So if we divide with 10, so what we get? 1, which is 103. That is simply the 10. Now moving to the next part. So what we get here, minus of that determinant, or you can say it is the center, 1 into 31 minus 1 into 103 divided by 1. Okay, 1 into 31 minus 1 into 103 divided by 1. So what you get? It is minus 72. For the next, it is the center too. So what we get? 1 into 0 minus 1 into 0 divided by 1. So we are getting 0. Similarly, for the next part, we will get 0 because it will be represented as here 4 by 4, right? 4 by 4 because we have the power s equals 0. Now for s power 1. So we will be starting with, let me clear, we will be starting with this one is, okay. So what we get here, minus 72 into 103 minus 0 divided by minus 72. So obviously it will come in plus 103. Now this one multiplied with this one minus it, then divided by minus 70. So we are getting 0, this will be 0. Finally, from this route table, we have to observe the first column, that is called route array. Okay. So what is our observation from this first column? Our observation is first entry is 1, then minus 72, then 103. Right? If it is so, so what we get here? There is no sign change. There is sign change. One time sign change. There is second time sign change, minus 72 to 103. So second time sign change, second times. So we got here first time sign change, second time sign change. From 1 to 72 to minus 72 to 103. That's why from the first column route array, what we get that two times unchanged. That's why system obviously is unstable with the two poles at the right hand side of the system. That is directly we can say map that the system is stable and having with the two pole at the right hand side of the system. Right? Now, so it is very easy process, no difficulties is there. Okay, if this kind of transfer function and as well as the characteristic equation available. Now there may be certain difficulties for the different types of system. Let it analyze. Now moving to the next part. So route Harvey's criteria for special cases. How it will be modified that. The basic route table checks fails in the following two cases. So what are the case? Number one, if zero only in the first column of any row. Of any row, if consisting zero, because see for any row for the first column that will be the denominator for the next one, right? So that's why let's see. See, this one is the denominator for the next one. So if it is zero, so that will become infinite. Okay, so there is a difficulty. So that's why there's one difficult case number one when zero is only in the first column of the row or entire zero consisting entire zero, entire column, entire row consisting zero. Suppose entire row having zeros, right? That will also be observed in the special cases. For special type of system that will be observed. There's experimental observation. While we will get all the any one entry to be zero in the first column, this is the special case, as well as all the entries in the first column is zero, that will be the special case, and that special case leads to certain comment of the system. Okay, we are coming. So move to the next part. So for the first difficulty, okay, so case one, first element of any row of the route array is zero. So what will be the generalizing formula be prescribed? That is, replace the first element, zero element, with a small positive integer. That means we are not considering the zero as zero. We are considering zero to be a very small positive quantity, that is epsilon. Zero to be a small positive quantity, that is epsilon. Okay, plus d. Then continue the process of completing the route table. That means if there is any zero arises in the first column, that will be regarded as epsilon, and then your route table will continue as same as the previous. Now find the number of sign changes in the first column of the route table by submitting epsilon tends to 0. So you just limit epsilon tends to 0 and you can conclude your route table is first array is providing all the entries are positive or negative or any sign change. Okay, let's take an example with the characteristics equation. S power 4 plus 2s cube plus s square plus 2s plus 1 that is equal to 0. Suppose. So we are taking one example. So we are moving to the route array. So what is the array formation? Is to the power 4 adding 1, then skipping this one, 1, then 1, 1, 1, 1. And for the second row, what will we get? 2 starting, then skipping this one, 2, 2. Okay, just so 1, 1, 1 for the first row and for the second row 1, 1. So s to the power 4 starting and then it will be into s to the power 0. So we have to move to get the next entries of the next row. So what we find here, just dividing both row element by same factor 2. Okay, for the simplification purpose. So what you get? 1, 1. Then continue the route array. So what we find? 1 into 1 minus 1 into 1. That means 1 minus 1. Divided by 1. So we are getting 0. Now 1 into 1 minus 1 into 1 minus 1 into 0, then by 1, that we are getting 1. Okay, so for the first route array we are getting here 0 entry, route array with 0 entry. So this is the difficulties. Then what we have to do, we have to route suggests that that may be considered as a positive quantity epsilon. So we are considering here 0 as a positive quantity epsilon. Then we will move. So how to move? Again starting with this epsilon and then this was the entry. So 1 into epsilon minus 1 into 1 divided by epsilon, that will be for the next column, and then it will be 0 obviously for the next element, that will be 0. So this will be 0, this will be 0, that is continuing. Then for the next part, next column, next row, what will we get? This is epsilon minus 1 by epsilon, right? This is our new center into 1 minus epsilon into 0 divided by this. So what will we get? We will get plus 1, right? Now, what is the resolution? Epsilon you have to take to 0. So what will you get? What will be the value? Let's see. That is clarified in the next table. So what we observe, that will be minus infinite. Very simple. So if it were may be declared as plus infinite, then there is no sign change. But it is minus infinite. That's why what is the sign change? No sign change, no sign change. Then we have the sign change one time. Then we have again minus one to minus infinite to one. Another sign change. So there is two times sign change. So two times sign change declares two right hand pole. Right hand pole. Plain and simple. Two right hand pole. So two times hand change, that means two right hand pole. So we can say system is unstable, totally unstable with the two right hand pole. Okay. So in this way, the first case of route array, that was the first element of any row, if consisting 0, that will be declared as infinite epsilon is a positive quantity, very small positive quantity. Then we will continue the route array same as the previous, and if limit epsilon tends to 0, so what we found here, it is minus infinite. Okay. So in this way, it will continue and we can conclude regarding the system stability of that control system. Okay. Now this is first difficulty that has overcome. Now coming to the next difficulty. What is the next difficulty? All the elements of any row will be 0. Let's take an example. So what we could do in that case. Okay. So our approach will be, we have to write the auxiliary equation of that row which is just above the row of zeros, that we will do. Again, we have to differentiate that auxiliary equation with respect to s. Then we will get the cofactors of that equation. S having the cofactors. Then these cofactors that will replace basically the above zeros. Okay, and then the out array will continue as same as the previous. Let us move and then construct the table. So for this equation, s to the power 5, starting with s to the power 5 with the cofactors 1, then skipping s to the power 4, we are getting s cube 1. Then skipping this one, we are getting s1. So 1, 1, 1. And for the next row, we are getting 3, 3, 3 cofactors. Okay. So it is 1, it will be 1, it will be 1. And for the second row, 3, this will be 3, this will be 3. If this is the characteristic equation. Let's see what I have written over there. 1, 1, 1 for the first, starting with s to the power 5, that will end to s to the power 0. Okay. So just getting the lower order one by one. So s to the power 4 column is 3, 3, 3. That will be divided with the common factor 3. So we are getting 1, 1, 1. So s cube, what we will get for the cofactors? 1 minus 1 into 1 minus 1 into 1 divided by 1. That will become 0. 1 into 1 into 1 into 1 minus divided by 1. That will become again 0. So in this way, we are getting row of zeros. So what is row of zeros? That is SQ row, that is row of zeros. Okay. Now what is our duty next? So this row of zero will observe for a certain kind of system and coming later on in conclusion. So what we have just above the row of zeros. So what are the cofactors we observe? Entries 1, 1, 1. Now this is the factor correspond to s to the power 4. So we have to make the auxiliary equation. This is the method. Okay. So we have to make the auxiliary equation and with the cofactors of just row above the zero rows. Okay. Rows of zeros basically. So what we get here, s to the power 4, then missing one factors because our frame or format of the route table is that we are just keeping one factors. Okay, s factors. So it is s to the power 4. It is corresponds to s square. It corresponds to s to the power 0. So we are writing over there s to the power 4 into 1 plus s square into 1 plus 1, that is equals to as. So it's a function of s. That's why it is called the a function of s, that is as. You may write and it is auxiliary equation. just using the cofactors above the zero rows. Okay, rows of zeros. Now we have to take the derivative with respect to s. So what we get? Let's see. So we are taking the derivative of as. What we find das by ds that will become 4s cube, that will become 4s cube, and 2 plus 2s that will become 0. Okay. So what are the coefficient we got? 4 and 2. 2, 4, 4 and 2. Just above the row of zeros. So what we get? This was the row of zeros. So we put here this is just above the row of zeros. Okay. So this will be 4 and 2. So we are putting here 4 and 2. So what we get here? This 0, that was 0 now. Let's see the previous slide. What is the row of zeros? Third column was the row of zeros. Okay, so we replace those two factors over there, 4 and 2. Just moving it here. So what we found here, we are getting here 4 and 2. And again we are dividing by the dividing rule. So we're dividing with two common factors, that will become 2 and 1. Okay, again constructing the route table, continuing the route table. Okay, so this will be the center, then 2 into 1 minus 1 into 1 divided by 2. Then 2 into this one minus 1 into 0 divided by 2. So we are getting these two in place. 0.5 and this is 1. Again for this one, s square column corresponds to 0.5 into 1, this one minus 2 into 1 divided by zero point 0.5. Similarly, 0.5 into 0 minus 2 into 0 divided by, so that will become 0, that will become 0. Again, we are getting here minus 3. And then we will again construct minus 3 into 1, then zero point 0.5 into 0 divided by zero point 5. So we are, sorry, that is divided by minus 3. So we are getting here 1. Minus 3 into 1 into 0, and this minus 3 into 0 divided by minus 3. Okay, so we are getting here 1. So looking into the first array, now what we observe, looking into the first array, we observe that there is no sign change, there is no sign change, there is no sign change. But while we are replaced, this one will continue, we can continue. So we are continuing with the difficulties has removed, and then we are getting zero point 0.5 to minus 3. So there is one time sign change, and then minus 3 to 1, there is 7 times sign change. So 2 times sign change refers to right hand pole, right? To right hand pole. Okay, to right hand pole. So what is our resolution? As there are two sign changes in the first column of the route table after removing the difficulty, so what we got here, the system is not stable. Fine. If the system is not stable, all the roots were at the right left hand side pole was there. Okay, now there should be the pole that should be at the right hand side or over the geometric axis. Okay, in this case if we analyze, what we'll find basically row of zero, that's a very important term. Row of zero only occurs for those systems that are having the complex conjugate pole. They are just pure imaginary on the imaginary axis. Complex conjugate pole here. J omega, and minus j omega. Complex conjugate pole here. If it is the case, only there will be the row of zeros occurs in the route table. This is the experimental observation. So in that case, suggestion is that you need to find that complex frequency such that system will become oscillatory or marginally stable, right? So what will be the response graph we will get in that case? CT versus T graph we will get, that will be the marginally stable case that I have expressed in the previous class. So what we got, it is the marginally stable case or oscillatory output, but having with some definite value. It is not indefinite, definite value, so marginally stable case. So we need to find here plus minus j omega, that pole position And here omega will refers that complex frequency, that particular frequency. Now what will be the next step? The next step is that will be the derivative, whatever we have taken, that is 4s2 plus 2s, that should be equal to 0. Okay, so what we get here, if we factorize this one, we will get s equals to 0. There is one pole at the origin, and then 4s square plus 2. So 4s square plus 2, we are getting here plus minus root under 0.5 j. Okay, so this is the marginal stable condition where we are getting omega, that is the complex frequency, that will be 0.5 root under. Okay, rad per second. Rad per second is very important numericals also for your exam. So it's very important. Okay, so that complex frequency you need to find. So where the system will be oscillatory, it is the sinusoidal output we are getting, and what is the constant, what is that frequency you need to find, the complex frequency. Here it is 0.5 rad per second. Okay, and what is your conclusion? Your conclusion is the marginal system is becoming marginally stable. System is becoming marginally stable. Okay, so today is beyond scope of other numericals. So route array we are continuing. Okay, so you may say for this case we are getting the auxiliary equation, and we will find the complex conjugate pole, basically complex pole pair, complex conjugate pole pairs for this case. Okay, so in this way we can say from the route array also we are getting the information the system is stable or not, as well as we are encountering that what will be the number of right hand side pole close to close meaning, because we are dealing, the route array is dealing with basically the characteristics equation. Okay, that is characteristics equation means basically the what you can say the closed pole position. So obviously the system stability that will be declared, as well as what will be the number of poles at the right hand side, that will be declared. Okay, as well as marginal stability condition that may be analyzed through route array. Okay, so today we have to stop over there, and then in the next class, some numericals, that unknown numericals will be presented. Thank you for today.